All right, in this video, we are going to do section 7.8, which is the last section in chapter 7, and it is titled Improper Integrals. So what we're going to look at is a couple of different types of integrals that we have to be able to approach that kind of cause some issues that we haven't quite seen yet. So let's begin with what most people think is the easier type to do, which is called type 1, and it is called infinite integrals. And it sounds just like you think it would. What happens if your interval needs to go to infinity or negative infinity and you need to work it out? So let's consider the infinite region S that lies under the curve y equals 1 over x squared above the x-axis and to the right of the line x equals 1. Well, in other sections, we could have already worked this problem depending on what our b value is. If, as you can see on these first three graphs here, if we had started at 1 and said gone to 2, or gone to 3, or gone to 5, we could have integrated these the exact same way, and there wouldn't have been any issues. The question we're going to see is that what happens when this b value shoots off towards infinity? Is it still possible to find the area under the curve? And the answer to that is it can and it cannot be. It's going to depend on the kind of function that we're given. What our ultimate goal is going to be in this section is that is there a way to express the area under a curve in a general form? So what we could do is we could have shown that the area under the curve of this function from 1 to any value of t is found to be 1 minus 1 over t. And then you could have plugged your t value in for whatever it may be, and you'll get your value. And as you can see from here, if t approaches infinity, and you plug infinity into this, that is where this area of 1 comes from. Now, is it always necessary to write your expression in terms of t's? No, but it is something we'll have to be able to do to solve certain improper integrals. So here is how we will officially solve an improper integral, and then I'll talk about maybe a shorter way. So if you are trying to integrate from a to t of f of x dx exists for every number, then what we can say is that the integral from a to infinity of a function is the same thing as the limit as t approaches infinity from a to t of the function. You will essentially change your infinity to a variable t, and then you'll integrate the same way we always do, and then apply the infinite limit at the end. It's almost identical if you do negative infinity. So if you're going from negative infinity to a b value, then you would change your negative infinity to t, and you would do the integral the same way, and then you would apply the negative infinite limit of the integral result. In the end, what you will end up getting here is that if you are able to solve either one of these integrals, then we can say that the improper integral is defined as being convergent. Versus if it's not possible to solve the integral, or if you get a limit that does not exist, then you will say that your improper integral is divergent. While we won't see this case all the time, there is instances where it may be easier to break up your infinite integrals into two easier integrals, but that may not come into play until later. So something we'll see a little bit later on is that if you're going from negative infinity to positive infinity on your integral, you could find a specific a value to break up your interval and evaluate two separate integrals to get your final result. That really only shows up when there's an issue somewhere in your interval, and we'll run into that in type 2 improper integrals, and I'll come back and kind of explain this a little bit more detail. Now, is it always necessary to do the long limit definition? Not in type 1. So if you're just trying to integrate from a number to infinity, as long as there's no continuity issues in your interval that you're checking, then you can just integrate this like normal. For example, determine whether the integral from 1 to infinity of 1 over x dx is convergent or divergent. Something that I always kind of look at kind of in my head is I ask myself, what can x not be? And since x, the only restriction here is going to be 0, 0 is not in the interval that you're going to be checking. That's great news, because what that means is that we can just integrate this like normal, because the integral of 1 over x is the natural log of x, and I'm going to evaluate that from 1 to infinity. So this would be the ln of infinity minus the ln of 1, which is equal to infinity minus 1, which is infinity. Since that is not an actual area that you can find, it means it's not possible to find the area under the curve, and therefore it is divergent. This is how you'll know you have a divergent improper integral. But that brings up a new kind of special situation. I showed you the 1 over x squared on the last slide, and we talked about that it's possible to find a finite area. But with 1 over x, we showed that the area is actually infinite. What ends up happening here is that just because your function is getting smaller and smaller, and eventually the area gets smaller and smaller, does not mean you'll always be able to find the area as you approach infinity. Sometimes you'll get an infinite area, but sometimes you can get a finite area. And that's the difference between doing convergence and divergence. So what rule can be applied here? Well, if you are trying to integrate from 1 to infinity of the particular function 1 over x to the p, it will always be convergent if your power of p is greater than 1, and will always be divergent if your power of p is less than or equal to 1. So in our cases, on the first one, your power was 2, that's why it was convergent, and your power was 1 on the second one, which is why it was divergent. Now, we may run into this rule again later, and we will definitely use it to help us out if it so much suffices. So now what I'm going to do is we're going to run through a variety of different type 1 improper integrals, and we're going to see whether or not they converge or diverge. So let's begin with the integral from 0 to infinity of 1 over the 4th root of 1 plus x dx. So I'm going to integrate this the exact same way like I normally would, and we're going to see whether or not it converges or diverges. This looks like a u substitution problem to me. So I'm going to let u be the inside of my 4th root, which is 1 plus x, and therefore du is going to equal dx. Even though it's an improper integral, since you are doing u substitution, you will have to change your parameters. So you'll plug the 0 and the infinity into here. 1 plus 0 is 1, and 1 plus infinity is infinity. This is 1 over the 4th root, not the root, sorry. I'm thinking u and wrote u instead of writing 4. That would be the 4th root of u times du. This can now be written as 1 to the infinity. Now the 4th root of u is u to the 1/4, and then if I flip that over, this would be u to the negative 1/4 du, which that can be integrated into u to the 3/4 multiplied by the constant 4/3 evaluated from 1 to infinity, which is equal to 4/3 times infinity to the 3/4 minus 1 to the 3/4. In the end, no matter what you do here, this is going to end up being infinity as a final result. So therefore, it is not possible to find an exact area under this curve between 0 and infinity. So therefore, your final result is divergent. And that is how you know it's a divergent improper integral. Let's look at another example. So example number 3. Determine whether the final integral converges or diverges and evaluate it if it converges. So how about the integral from 2 to infinity of e to the negative 1 over x, all divided by x squared? So when I go to set up my integration here, this once again looks like a u sub problem because that 1 over x is not something I know how to integrate if it's part of the e. So I'm going to let u be negative 1 over x, which is the exact same thing as negative x to the negative 1. Therefore, du would end up being x to the negative 2 dx, and dividing that over would say du over x to the negative 2 is equal to dx. Once again, I'm going to change my parameters here by plugging my 2 and my infinity into my u function. So negative 1 over 2 is negative 1/2, and negative 1 over infinity would be 0. This becomes e to the u over x squared times my dx term, which is du over x to the negative 2nd. Very nicely, those x's actually multiply and cancel each other, and you just have the integral from negative 1/2 to 0 of e to the u du. All right, so if you integrate that, it just becomes e to the u that I'm going to evaluate from negative 1/2 to 0. This will become e to the 0 minus e to the negative 1/2, which is the same thing as 1 minus 1 over root e. And while that is not a perfect number, it is still a finite value that we can find under the curve. So the area under this curve from 2 to infinity is possible to find. So therefore, as long as you really don't get positive or negative infinity, you will always say that it is a convergent improper integral. All right, example number 4. What is the integral from 2 to infinity of 1 over x squared plus 3x minus 4? So this is no longer a u sub problem. This looks more like a possible partial fraction problem that we did back in section 7.4. Because remember, it's probably going to be a partial fraction if you're able to factor the bottom. And x squared plus 3x minus 4 would factor into x plus 4 times x minus 1. So I need to break this up in order to solve this problem. So this is going to end up being, so we're going to take 1 over x plus 4, x minus 1. This is a case 1 partial fraction, so I would break it up into a over x plus 4 plus b over x minus 1. I'm going to multiply everything by the factored denominator. Remember, you distribute it to all 3 terms. This would end up giving me 1 equals a times x minus 1 plus b times x plus 4. And since it's a case 1 partial fraction, we can actually use that little technique called the plug and chug method I showed you. So if I were to let x equal 1, I could say that 1 is equal to 5b, which means that b is going to be 1/5. Then if I let x equal negative 4, I could say that 1 equals negative 5a, so therefore a is negative 1/5. I can now rewrite my improper integral, and we are going to integrate from 2 to infinity of negative 1/5 over x plus 4 plus 1/5 over x minus 1. Both of those integrate into natural logs because the derivative of the bottom of each one is just 1. So this would actually be negative 1/5 times the natural log of x plus 4 plus 1/5 times the natural log of x minus 1, evaluated from 2 to infinity. Now, one thing to note here is that when you're doing these infinite parameters on natural logs, you're going to run into an issue that you're going to have to go ahead and fix. And I would go ahead and just fix it now. I would go ahead and combine these natural logs because it'll be easier to evaluate the infinite term. So I'm actually going to rearrange them. So why don't I do this? Why don't we call this 1/5 the natural log of x minus 1 minus 1/5 times the natural log of x plus 4, evaluated from 2 to infinity. I could then combine these because they both share a 1/5 in common, so I factor that out front. And then since both natural logs are being subtracted, I could write this as the natural log of the first divided by the second that we will evaluate from 2 to infinity. Leaving the 1/5 out front, if I were to plug infinity into this natural log, since the power on top and bottom match, you can just use the ratio of coefficients, which would make this the natural log of 1, minus, if you plug in 2, this would be the natural log of 1/6. Well, very nicely, the natural log of 1 is just going to be 0, and if you distribute the 1/5 through, you get negative 1/5 times the natural log of 1/6. And since that is an actual area that you can find under the curve, this is another example of a convergent improper integral. The big thing to note in this section, and I warned y'all when we ended section 7.4, is that there aren't any new rules, but any rule that we've covered so far will show up over the next few sections as we apply different ideas. All right, let's do a couple more and then we'll move on to type 2 improper integrals. So number 5, what is the integral from negative infinity to 0 of x times e to the 3x? This is our first time seeing one with a negative infinity, but it doesn't change our approach to how we will work this problem. So first off, you got to figure out how to integrate this. Since, let's see, u sub's not going to work because the powers match, but since these two terms are being multiplied, if u sub doesn't work, your next instinct is probably to do integration by parts. But the nice thing about this integration by parts is that it can actually be done with tabular method. Because if you take the derivative of x, you will eventually get to 0 after 2 repetitions, which means you need to integrate that many times as well. So e to the 3x integrates into 1/3 e to the 3x, which then integrates again into 1/9 e to the 3x. We'll alternate our signs and we will multiply at the diagonal. So that means that my integral actually turns into 1/3 x e to the 3x minus 1/9 e to the 3x that we are going to evaluate from negative infinity to 0. So if you go through and plug 0 into both of these, you will end up getting 0 minus 1/9 minus, if you plug negative infinity in, this is the tricky part, because you're going to get 1/3 times negative infinity, but e to the negative infinity is actually going to be 0. That's not good. We'll fix that in just a second. Minus 1/9 times e to the negative infinity is 0. So in the end, this term's not actually here. This first parenthesis becomes a negative 1/9, and then you're going to end up with a plus 1/3 times infinity times 0. This is something that you should have seen in a Cal 1 class when you did indeterminate products of limits. You're going to have to figure out what happens when you multiply a 1/3 times infinity. So where did this come from? This came from solving this problem right here as an infinite limit. All right. So over here on the right, I'm going to have to write out the limit as x approaches infinity. Now, the reason I'm not doing negative infinity is because the negative that I plugged in here canceled with the negative in the front. So you can do it as a positive here. And then you're going to do 1/3 x. Actually, I don't even need to do the 1/3. We just need the x part. So this would end up being x times e to the 3x, because the 1/3 can just stay there. Well, since that's infinity times 0, I need to flip one of those over. It doesn't really matter which one. I usually just flip e's over when this happens. So I can rewrite this as x over e to the negative 3x. So this allows me now to do L'Hopital's rule, because this right here would be infinity over e to the negative infinity would end up being, where are we at here? So this is going to end up being, sorry, I need to do the negative infinity here. So negative infinity. So that would end up being negative infinity over infinity, which allows us to do L'Hopital's rule. Sorry about that. I still got to do the infinite number here. All right, so doing L'Hopital's rule lets me, this becomes the limit as x approaches negative infinity of 1 over negative 3e to the negative 3x. And if you plug negative infinity into this, it will be 1 over negative 3. E to the positive infinity would be infinity, and this whole thing is going to go to 0, which means that in the end, the 1/3 times infinity times 0 will end up becoming 0 that we verified using L'Hopital's rule. So after all is said and done, everything cancels except for the negative 1/9, which allows us to once again say that this is a convergent improper integral. All right, so let's do one more type 1 improper integral, and then we'll move into the type 2s. So here's an example of where you have a negative and positive infinity in your parameters. So what is the integral from negative infinity to infinity of 1 over 1 plus x squared? Since no numbers in the bottom make this undefined, you don't have to rewrite anything. You can just directly integrate this and evaluate. So this would end up being 1 over 1 plus x squared is one of your rules you should know. It is the inverse tangent of x that I am going to evaluate from negative infinity to positive infinity. So this would become the inverse tangent of infinity minus the inverse tangent of negative infinity, which are values that you're supposed to remember when you did this type of stuff in Cal 1 and from trig. You should get pi over 2 minus a negative pi over 2, which is the same thing as pi over 2 plus pi over 2, which gives me a value of pi. That is a value that you found under the area of the curve. So once again, this is a convergent improper integral. And that is definitely the more popular way of doing these. These are called type 1 improper integrals. They work out very nicely because it doesn't require any rewriting. You can go directly into your integration. What we're about to get into is type 2 improper integrals, and those are a little bit more painful to do because you're going to have to rewrite some stuff in order for this to work. So let's talk about what a type 2 improper integral is. These are also called discontinuous integrands or integrals, which means that there is a value in the interval that you're checking that's going to cause it to be discontinuous. That usually happens when there's an asymptote involved. So if there's a vertical asymptote somewhere in your interval, you're going to have to fix that before continuing. So let's first suppose that we have a function, and it's a positive continuous function defined on a finite interval a to b, but at your right endpoint, what if it has a vertical asymptote there? So you see right here on the endpoint, there is a vertical asymptote involved. Well, you can't integrate from a to b because b does not actually exist when it comes to the function. So what you will have to do is to find the area under this curve. You will have to integrate from a to t, because we're going to let t be any number less than b of the function. The problem is that you can't just pick a random t. You've got to put this t as close as possible to your asymptote as you can to get the best approximation for your area. Which means that since this t value needs to get as close as possible to b on its left-hand side, we will rewrite this, and in front of our integral, we will put a limit as t approaches b from the left of the integral from a to t of f of x dx. So you will work out the integral in a general sense, and then you will apply the limit to what you find as your result. Now, is this the only way to do it? It is not. As you probably can guess, what happens if there's an integral on the left-hand endpoint? We're going to talk about that. And even worst case, what happens if the asymptote falls somewhere in between your a and b? We need to know how to approach each of those individually so that we can tackle how to actually solve them. All right, so type 2 improper integrals. Let's go through all three situations so that we can actually find them. I'm not going to go through part 1 again because this is the way I just talked about. If your vertical asymptote is on the right endpoint, you will replace your upper parameter with a t value, and then you will do the limit as t approaches b from the left. If your asymptote falls on the left endpoint, which means that a value has an asymptote, then instead you would do the limit as t approaches a from the right of the integral from t to b of f of x dx. That's because if you think of it, I'll use a little line graph right here. If you think of it as the integral from a to b, you want to approach a as close as you can from the right-hand side. That's why we do a right-hand limit when it's the left endpoint that's discontinuous. And then we're going to see one in a few minutes. It's probably the worst case scenario. It's part C. If there is a discontinuity in the middle of your interval, you will have to break your integral up into two separate integrals. And you'll have to do the integral from a to c plus the integral from c to b. And this one you would work like part A, and this one you would work like part B. So you'd have to do both parts in one problem to get the overall answer. Once again, if you can actually find an area under these curves using these techniques, we will say that it's a convergent improper integral. Versus if it's not possible to find the area under the curve, or if you get a limit that does not exist, we will say that our area is divergent and not possible to find. And I'm going to show you an example of each kind. One where the right endpoint is your asymptote, one where the left endpoint is your asymptote, and then one where it falls somewhere in the middle. That way you know how to approach each idea. All right, so let's start with this one. What is the integral from 0 to 1 of 1 over the square root of 1 minus x squared? So the difference in this one from the first 6 problems that we've done today is that one of these parameters is not going to be able to be plugged into the original function. And in this case, that would be the number 1. If you try to plug 1 into this function, you would get an undefined value. That's why this is a type 2 improper integral. So since it is the right endpoint, I will have to write this as a limit as t approaches 1 from the left-hand side, and then I will replace the 1 with a t in my integral. Everything else is going to be exactly the same. 1 over the square root of 1 minus x squared. Integrate this. So you're going to do all the integration stuff, and the limit will just come along for the ride. This will be the limit as t approaches 1 from the left. This integrates exactly into an inverse sine function, which we're going to evaluate from 0 to t. This will become the limit as t approaches 1 from the left. So plug your upper parameter in, and that's inverse sine of t minus the inverse sine of 0. Now, inverse sine of 0 is just 0, so that term actually goes away. Once you have fully simplified your integral, you will then take your limit value and plug it into the function. So this would be the inverse sine of 1, which is equal to pi over 2. Since that is an actual finite area that you can find, this is going to be a convergent type 2 improper integral. If you had gotten like infinity or negative infinity or d and e, that's when you would say it's divergent. But very good. That's how you'll approach if the right endpoint is your asymptote. All right, set it just like that. Integrate the same way. Set it up. When you're done integrating, you will evaluate it at the limit as t approaches whatever it ends up. All right, what about number 8? What is the integral from 0 to 9 of 3 over the cube root of x minus 1 dx? So this is the worst case scenario, I would probably say, because if you look at your original function and look at the bottom, the number that cannot be plugged in is the number 1. Because if you plug 1 into the denominator, you will get an undefined function. But the 1 is not one of your endpoints. The 1 is right in the middle of the interval from 0 to 9. So what you will have to do here is you're going to have to rewrite this as 2 separate intervals. We're going to go from 0 to 1 of 3 over the cube root of x minus 1. And then we're going to add to that the integral from 1 to 9 of 3 over the cube root of x minus 1. Now, each of these are now separate type 2 improper integrals, so we got to break both of them up at the discontinuous point. So this would be the limit as t approaches 1 from the left, because the 1 is the upper parameter, and that's the problem. Then we're going to integrate from 0 to t of 3 over the cube root of x minus 1 dx. Then I'm going to add to this another limit, but this time I want to do 1 from the right because it's the lower parameter of your second integral, which will go from t to 9 of 3 over the cube root of x minus 1 dx. Now, the one good thing about both of these is that even though they are separate problems you have to work, you're going to actually integrate them the same way throughout the entire process. So both of these are going to be u subproblems. So I'm going to let u equal x minus 1. So therefore, du is equal to dx. But you will have to change your parameters on both sets of integrals. So if I do the limit as t approaches 1 from the left, if I plug 0 in, that gives me a negative 1 lower parameter, and plugging in t would give me t minus 1 of 3 over the cube root of u times du. Plus, you would have the limit as t approaches 1 from the right. This would then be from t minus 1 to 9 minus 1 is 8 of the same thing, 3 over the cube root of u du. All right, each of these can be rewritten. So this would be the limit as t approaches 1 from the left of the integral from negative 1 to t minus 1 of 3 times u to the negative 1/3 du, plus the limit as t approaches 1 from the right of the integral from t minus 1 to 8 of the same thing, 3u to the negative 1/3 du. Integrate them both the exact same way. So we're going to have the limit as t approaches 1 from the left of, so that's going to be u to the 2/3. And if I multiply the 3 by the reciprocal of that, you should get 9/2 that we're going to evaluate from negative 1 to t minus 1. Plus, you're going to get the exact same integration, but you have to do 1 from the right of 9/2 u to the 2/3, evaluated from t minus 1 to 8. All right, so let's see. On the first one, if I were to factor that 9/2 out front, and actually I can factor a 9/2 out of the whole thing because they both share the same common constant, that's going to end up giving me the limit as t approaches 1 from the left of t minus 1, that's going to be t minus 1 to the 2/3 minus negative 1 to the 2/3. All right, plus the limit as t approaches 1 from the right of 8 to the 2/3 minus t minus 1 to the 2/3. And all of that's inside the same bracket. So when you try to plug your limits in, when you try to plug 1 into this first t, 1 minus 1 is going to be 0, and 0 raised to the 2/3 means that term's going to actually go away. Likewise, on your last limit, when you apply it to the t minus 1 to the 2/3, that also goes to 0, and you're just left with all of the constants that are inside. So you're done with your limits. This would be 9/2 times, all right, so negative 1 to the 2/3 is going to be 1, but there's a negative in the front, so that makes it negative 1, plus 8 to the 2/3 would end up being 4. Negative 1 plus 4 is 3, and 3 times 9/2 is going to give you a final answer of 27/2, which then shows us that this improper integral is also convergent. But we had to break it up into two separate integrals because the discontinuity occurred in between our a and b value. All right, and last but not least, let me do one where your left endpoint is going to be the problem. So what if you're trying to integrate pi over 2 to pi of tangent squared of x dx? Well, as far as a tangent function goes, pi over 2 is undefined when it comes to a tangent function. So squaring undefined is still going to be undefined. So pi over 2 is our issue here. Let's rewrite this as our limit problem. This would be the limit as t approaches pi over 2. Now, since it's on the bottom endpoint or the left interval, you have to approach from the right of the integral from t to pi of tangent squared x dx. Now, you can't integrate tangent squared directly, so you'll have to use an identity to help you out here. So what I remember back from my Pythagorean identities, let's get all this limit stuff down, is that tangent of squared is actually equal to secant squared x minus 1. We did that a lot back in section 7.2 when we were doing trig integrals. Both of these terms can now be integrated. So now we can go about our integration technique. This would be the limit as t approaches pi over 2 from the right of secant squared integrates into tangent of x minus 1 becomes x, and you're going to evaluate this from t to pi. So this will equal the limit as t approaches pi over 2 from the right. If I plug pi into both of those, that would be the tangent of pi minus pi, and then minus this would be the tangent of t minus t. Now, of those values, tangent of pi is actually going to be 0, so that term goes away. And then if I evaluate the pi over 2's here, so here's where you got to be careful. This becomes negative pi, and then minus the tangent of t, plus t, and all of this is going to be the limit as t approaches pi over 2 from the right. All right, so when you plug pi over 2 from the right into these, this is where you have to remember your basic tangent graph. So when it comes to a tangent graph, the normal asymptotes are at negative pi over 2 and pi over 2, and looks something like this. And then a tangent graph keeps repeating itself going to the left and to the right. So if you're trying to figure out what's happening to a tangent graph as you approach pi over 2 from the right, well, pi over 2 from the right is going to end up approaching negative infinity based on the graph of a tangent function. So if that's going to approach negative infinity, you're going to end up with negative pi minus a negative infinity plus a pi over 2. But in the end, these pi's don't really matter because since you have an infinity involved, the whole thing's going to end up going to positive infinity, which means that the area of this interval is not possible to find, and therefore you will get a divergent area. So when it comes to case 2, you can get convergent and you can get divergent depending on the situation. So that ends the video for section 7.8. So we did improper integrals of type 1 and type 2 variety. That also ends chapter 7. In the next video, we will start our lectures on chapter 8, which is just more application problems. So come back ready to integrate some more in a different way.